Look into the deep universe and you will see everything flying apart. But how fast is it expanding? For 30 years, astronomers have pointed their instruments at the night sky to measure that speed limit, and they keep coming back with two entirely different numbers. One group gets 67.5, the other gets roughly 73. And as our measurements have sharpened, the gap between those numbers has widened into a definitive 5 sigma disagreement. Think of the universe as a rising loaf of raisin bread. Sitting on one raisin, the expanding dough pushes every other raisin away. The farther a neighbor is, the faster it appears to recede. This recipe's rising rate is the Hubble constant. It is the master mathematical recipe that sets the age of the cosmos and the size of everything we can see. If our calculation for that rate is wrong, almost every other number in modern cosmology drifts with it. To find that number, scientists look at the universe from opposite ends of time. The first approach looks backward, capturing light that has been traveling for almost 13.8 billion years to study the cosmic microwave background, the faint afterglow of the Big Bang. This graph plots the subtle temperature variations embedded in that ancient radiation. By measuring the size and spacing of these acoustic ripples, physicists can predict what the expansion rate should be today, 67.5 kilometers per second per megaparsec. The second approach measures from the bottom up. Instead of looking back at ancient light, it builds a cosmic distance ladder directly across our local space. Astronomers climb this ladder step by step. They start by calculating the parallax of nearby stars, step up to pulsating stars called Cepheid variables to gauge distance by their predictable brightness, and finally track massive explosions known as Type Ia supernovae deep into the void. When you use this direct, local pipeline to measure how fast those distant supernovae are moving away, the math produces a much higher expansion rate of roughly 73. Both pipelines have been refined by hundreds of physicists for decades. Because both sets of tools are now ultra-precise, we are left with a binary reality. Either an invisible human error is corrupting the measurements, or the universe itself is not the shape we thought it was. For years, the physics community suspected that the distance ladder was simply flawed. Because Cepheids live in heavily crowded star fields, even the Hubble Space Telescope struggled to separate a target star from its neighbors. If that blurriness artificially inflated the apparent brightness of the stars, the distances would be slightly off, skewing the math higher. The James Webb Space Telescope was deployed to definitively solve this exact problem. Its massive infrared mirror was designed specifically to slice through cosmic crowding and view those Cepheids cleanly. In early 2024, a team led by Nobel laureate Adam Riess used JWST to observe over 1,000 of those exact same Cepheid variables, running the new optics and old Hubble photography side by side, star by star. The measurements matched perfectly. Webb and Hubble gave essentially identical distances, ruling out measurement error at an 8.2 sigma confidence level. The telescope built to clear up the blur definitively proved that the discrepancy is real. This is no longer a statistical tension. It is an active crisis. It forces cosmologists into uncomfortable territory, asking exactly how we have misunderstood the cosmos. Our standard model of the universe relies on a strict recipe: a sliver of ordinary matter, a large chunk of dark matter, and a dominating pressure of dark energy. If the observations are correct, that recipe is missing an ingredient. The leading fix is early dark energy. It proposes a sudden extra push of pressure right after the Big Bang. This shrinks the acoustic ripples we measure. Recalculating the ancient light with these shrunken waves slides the 67.5 prediction up to match 73. But making the math work on paper highlights a frustrating irony. Dark energy is already just a label for a phenomenon we can't fully detect. Early dark energy is an unproven placeholder bolted onto another placeholder. There is something incredibly humbling about this moment in precision physics. We built an observatory the size of a tennis court, folded it into a rocket, and we sent it 1,000,000 miles into the cold dark of space, all just to ask the absolute simplest question imaginable. The universe answered by breaking our best models. But discovering we are wrong is exactly how science moves forward. If you want to keep exploring this cosmic mystery, hit the subscribe button so the next deep dive lands in your feed. Check out the related videos to see more JWST discoveries, and drop your own theories on the Hubble tension in the comments. Thanks for watching, and as always, look up.